Okay, chapter 1 is on polynomial functions, and the first lesson we're going to be looking at is on the power function. So essentially we're going to look at three things in this lesson. The first thing we're going to look at is what a polynomial function is and what it looks like. Then we're going to talk about what a power function is, some of the properties of power functions and what they look like, and then we're going to end up with interval notation. So up to now you've studied two polynomial functions in detail. These are the linear and the quadratic polynomial functions, so you're familiar with the way they look. How do you recognize a polynomial function? Well, polynomial functions have exponents that are whole numbers. They may not be written in rational form unless the denominator is a constant value. So there's some examples here that I've written down. And so this part here where it says the polynomial function may not be written in rational form unless the denominator is a constant value. So the only time you can have a fraction in a polynomial function is if the denominator of the fraction is just a number. Okay, so I have three examples here. In the first example, you'll notice that the exponents are both whole numbers, and that the rational part here has a constant term at the bottom. So this is a polynomial function. Okay. In the second one, you'll notice that this has a whole number exponent. This one also has a whole number exponent, but the problem is that the denominator does not have a constant value. Instead, it has a variable. So this is actually not a polynomial function. And then the last part here, it says exponents must be constants, not variables. And you'll notice in this example, the exponent that I have here is not a constant. It's not just a number. It's actually a variable. So again, this is not a polynomial function. Okay. So some more for the polynomial function. So the definition of a polynomial function. Polynomial functions are functions that may be written in the form, and you see the form listed there. And so basically what's happening here is that you're starting with polynomial terms or power terms that go from the highest exponent and decrease in terms of exponents, or in other words, they decrease in degree. Okay. The A part that's at the front of each of the variables just represents the coefficient or the constant term. So here we'll talk about what each of these variables mean. X is an element of all real numbers, which means X is just an element of all real numbers. AN to A naught are real numbers, so these are just the coefficients of the variable terms. And then AN is the leading coefficient. So what this means is the term that has the highest exponent on it, which is this term here, the coefficient of that is called the leading coefficient. Okay, and this helps talk about the behavior of the graph, whether it's increasing, decreasing, the direction that it opens, the end behaviors. So that's why the leading coefficient is important. A naught is the constant term, so it just looks at the numerical term at the end. Okay, and n is a whole number. The degree of the polynomial function is n, the exponent of the greatest power of x. So what this means is whenever you're trying to figure out what the degree of the polynomial function is, you're looking for the term that has the highest exponent, and that's the degree of the polynomial function. Okay, for example 1, it says consider the function below. So we have f of x equals 4x cubed minus 5x squared plus x minus 1. So this is a polynomial function, and you can see that because each of the variable terms have an exponent that's just a whole number. We don't have any fractions in this case. So part A says, what is the constant term? So what we're looking for is a term that has no variable part associated with it, and so that's here. So the constant term in this case is just negative 1. Okay, the sign in front of it is important. Okay, the leading coefficient. So we're looking for the term that has the highest exponent, and so this is the term here with the highest exponent, and the leading coefficient is the number in front of the variable for that term. So in this case, the leading coefficient is 4. Okay, and then what is the degree of this function? So again, look for the term with the highest exponent, and so that's this one here. So that means that we have a degree 3 polynomial function. Okay, so some more terminology. You're going to get a lot of terminology in this lesson. Line symmetry and point symmetry. So some of this you've seen a little bit in grade 11, and some of it's actually new. So just a new name for line symmetry. Okay, line symmetry. A graph has line symmetry if there is a vertical line, x equals a, that divides the graph into two parts such that each part is a reflection of the other in the line x equals a. So what that means is if a graph has line symmetry, there should be a line, a vertical line, that splits the graph exactly in half, and the left side and the right side of the graph should be exactly the same. So what this means is this red dashed line that I have here if I reflect the right side of the graph along that line, I'll get the exact same graph on the left-hand side. Okay, so that's line symmetry. Point symmetry is a little bit different. So you're looking at symmetry about a point. So a graph has point symmetry about a point AB if each part of the graph on one side of the point can be rotated 180 degrees to coincide with the part of the graph on the other side of the point. So let's say this is the point here, you see a red point here. What this means is if I actually take the right-hand side of the graph, or any of the points on the right-hand side, and I rotate it 180 degrees, what will happen is the right side of the graph will coincide with the left side of the graph. Okay, so that looks at point symmetry. So you're looking at rotating 180 degrees around one point. Okay, the next definition we're looking at is the definition of a power function. So this is what the section that we're looking at is actually about. So a power function is a polynomial function of the form f of x equals a times x to the exponent n, where n is a whole number. Power functions are single-term polynomial functions, so they only have one term, and they're polynomial functions but with one term. Power functions have similar characteristics depending on whether their degree is even or odd, and we're going to look at that in a couple of minutes. Okay, so here's some examples of polynomial functions. What you'll notice is the first one is actually a power function because it's a single term polynomial function, or in other words, this is just a quadratic function, and you can see that it's quadratic and it's a power function as well because it's just got one single term. Whereas the second one, it is a polynomial function, but it is not a power function since it has more than one term. Okay, so we're going to look at the graphs of power functions since they are related. Okay, depending on whether they have an even degree or an odd degree, or an even exponent or an odd exponent on the power function. So consider the following power functions. We have a linear function, y equals x, quadratic, y equals x squared, cubic, y equals x cubed, quartic, y equals x to the exponent 4, quintic is y equals x to the exponent 5, and sextic is y equals x to the exponent 6. And if you look at each of the red graphs, which are the odd degree polynomial functions, or the odd degree power functions, what you'll notice is that they all have the same kind of end behavior. Okay, as you go towards the left in the graph, all three of these graphs start to decrease towards negative infinity. So they're getting smaller and smaller and smaller. And you'll notice that's the same for the quintic and the cubic graph as well. And as you look at what happens to the graph as x approaches positive infinity, you'll notice that the right-hand side of the graph seems to be increasing towards positive infinity here. Okay, so if you look at the even degree power functions, so the quadratic, the quartic, and the sextic, what you'll notice is that each of these are related. And what you'll notice also is that they sort of have that symmetry. They all kind of look like a quadratic function. Okay, you'll notice that the end behaviors are the same. As x approaches negative infinity, the graph approaches positive infinity. And as x approaches positive infinity, the graph approaches positive infinity as well. So both ends of the graph go in the same direction. Whereas for the odd degree power functions, they go in opposite directions. One's decreasing, the other end's increasing. Okay. What the only difference is between the quadratic, quartic, and sextic that you can clearly see is what the behavior is close to that turning point in the graph, where the graph changes direction from decreasing to increasing. You'll notice for a quadratic, it's sort of like, looks more like a V. It comes down to more of a point. But as you look at a quartic, you'll notice that it's sort of flat here. And if you look at a sextic, it's even flatter. Okay, you'll notice that the graph is just steep on the two sides. Okay, so what happens is the higher the exponent on the actual power function, the flatter it is at the origin in this case. So you'll notice the cubic function and the quintic function as well. They both look the same, but the cubic function is not as flat as the quintic function. Okay, so some things to look for when you're looking at odd degree and even degree power functions. Okay, example 2 says consider each graph below. So we're going to have a list of questions that we're going to answer in regards to the graph. And I have the solutions written down, and so I'll just discuss it with you guys first, and then I'll move this slide up so you can see the solutions as well. Okay, so the first question says, does it represent a function of even degree or odd degree? And then explain. One of the simplest ways to determine whether a graph represents an even degree function or an odd degree function is to think about whether the behavior of the graph looks like a linear graph or like a quadratic graph. So a linear graph is the simplest odd degree function that you know, and a quadratic graph is the simplest even degree function that you know. So think about whether it looks like a linear function, or if it behaves like a linear function, or if it behaves like a quadratic function. So the first one here looks like it's behaving like a quadratic function, so I know it's going to represent an even degree polynomial function. Then it says state the sign of the leading coefficient. Well, when I think of the leading coefficient, I'll think about what the leading coefficient looks like if it was quadratic. If it was quadratic and it opened up, I know that the leading coefficient is positive. So because this is an even degree, then I'm going to assume that it's probably going to follow the same behavior, and so I'll know that the sign of the leading coefficient will be positive because the graph is opening up. In terms of the domain and range, you can see that the graph continues infinitely towards the left and towards the right, so the domain is all real numbers. And in terms of the range, it's got a minimum point here at 0, and so all the values of y are greater than or equal to 0. Okay, and y is still an element of all real numbers. Okay, identify any symmetry. I can see that there is some symmetry. I can see that there's a line symmetry along the y-axis, so there's line symmetry at x equal to 0. And then describe the end behavior. So as x approaches negative infinity, I can see that the graph is increasing, so y is approaching positive infinity. And as x approaches positive infinity, as I move towards the right in the graph, I can see that the y value is increasing, so again y is approaching positive infinity. For the second graph, it represents an odd degree polynomial function, and you know that because it's sort of following the same behavior as a linear graph would. The only difference is instead of your linear graph going up and to the right, this time it's coming down and to the right, which indicates to me that it might have a negative leading coefficient, sort of like what the graph of y equals negative x looks like. So when you look at y equals negative x comes down and to the right, and this is sort of following the same kind of behavior. Okay, so I know this is an odd degree polynomial function, and also because the graph is going in opposite directions. One end's increasing, the other end's decreasing. The sign of the leading coefficient must be negative since the graph is decreasing, it's coming down and to the right. In terms of the domain, you can see that the graph goes infinitely to the left, infinitely to the right, so that means all real numbers for the domain. In terms of the range, you can see that there is no upper or lower limit. The graph continues upwards and downwards, so the range is also all real numbers. In terms of any symmetry, there's no line symmetry because there's no line that the graph can reflect upon so that it coincides. But there is point symmetry, and you can see that that point would be at the origin. Okay, so the point symmetry is at 0, 0, and if I take the right-hand side of the graph and I rotate it 180 degrees, it'll coincide with the left-hand side of the graph. And then in terms of end behavior, as x approaches negative infinity, you notice that the graph is increasing, so y is approaching positive infinity. And as x approaches positive infinity, so as x is increasing, the graph is decreasing, so y is approaching negative infinity. Okay, so here's all the solutions to each of the questions.